Hi everyone, my name is Luca Rotta and I am a PhD student at the University of Milan in Italy. I am a member of Everywhere Lab, a research lab that works on data management for pervasive and mobile computing. Today I will present you the MARBLE Dataset, a dataset that we collected and that includes multi-inhabitant activities of daily living combining wearable and environmental sensors data. The recognition of activities of daily living, or just ADLs, in smart home environments is a well-known research area in pervasive computing. The accurate recognition of ADLs is crucial, for example, for healthcare systems that monitor the behavior of fragile elderly subjects in their homes. For instance, the sequence of ADLs performed by a subject and their execution modalities may reveal early symptoms of cognitive decline. Smart home ADLs recognition is typically based on the use of unobtrusive environmental sensors deployed in the home environment to monitor the interaction of the residents with their surroundings. Another possible approach is called video-based, as it monitors the residents by using cameras and microphones. However, such devices are perceived as too intrusive by the users. For this reason, we focus our research on sensor-based approaches. Most of the works in literature assume a smart home inhabited by a single resident. This scenario is realistic. However, multiple subjects may live in the same home, for example, a married couple of elderly subjects. In this setting, it is often necessary to identify both the individual activities performed in parallel, for example, Alice is watching TV while Bob is watering plants, and those performed by a group of residents. Alice and Bob are cooking together. The major challenge and open problem of multi-inhabitant activity recognition is called data association. The problem is that environmental sensors cannot automatically identify the resident that triggered them. So, how we can map each environmental sensor event to the resident that generated it? Let's make an example about the data association problem. Suppose that Alice and Bob live together and they are both in the kitchen. Alice is relaxing at the kitchen table, while Bob is cooking. The system recorded the two sensors events. The first one is a pressure sensor on the chair, revealing that someone is sitting at the kitchen chair. The second one is a magnetic sensor attached to the fridge door, revealing that someone is opening the fridge. So, the problem of data association here is how the system can infer that Bob is opening the fridge while Alice is sitting on the kitchen chair. In literature, the researchers have mainly focused on a single machine learning model that detects the most likely combination of residents' activities based on the observed sequence of environmental events within the smart home. In this case, the data association is implicitly learned by the model from the dataset in a data-driven manner. However, this approach suffers from scalability and portability issues. Indeed, in the training set, we should have examples for all the possible combinations of activities that the residents can perform together or individually. Hence, the complexity of the system increases with the number of residents and the number of activities that we need to recognize. In multi-inhabitant settings, wearable sensors can provide important additional information to improve scalability in data association. Indeed, a wearable, being a personal device, identifies the subject that is wearing it. Moreover, it can also reveal the proximity to environmental sensors when triggered, for example by taking advantage of an indoor repositioning system. At the same time, with wearables, we can expand the set of detectable activities. We can combine the physical movements of the subject with the environmental sensor events, and so it is possible to discriminate a larger number of activities. For example, sitting at the kitchen table, eating at the kitchen table, and drinking at the kitchen table. Moreover, wearable sensors can also monitor ADLs not captured only by environmental sensors. This is important considering that it can be too costly to deploy a significant amount of environmental sensors that can capture all the possible household items. Finally, we claim that, while constantly wearing devices may be considered unrealistic, smartwatches and wristbands nowadays are becoming quite common and they represent a non-intrusive technology that can be continuously worn in home environments. So we present the MARBLE dataset to speed up new research contributions in the poorly explored field of ADLs recognition in multi-inhabitant settings. Indeed, any new approach in this research field requires an empirical evaluation on labeled datasets. A limitation of most of the existing ADLs datasets is that they only include data from single inhabitant settings, and only few multi-inhabitant datasets are available. At the same time, the main reference multi-inhabitant datasets, cases and eras, have been collected in real home environments, inhabited by 2 subjects, but considering only environmental sensors. Hence, it is challenging to evaluate novel data association methods on these datasets. Today, we present MARBLE, a new publicly available dataset of ADLs performed in multi-inhabitant settings. MARBLE includes data from both wearable and environmental sensors. Moreover, it includes scenarios where up to 4 residents perform 13 different types of activities in the same smart home environment. Overall, MARBLE includes data from 12 different subjects, and it contains around 16 hours of labeled multi-inhabitant ADLs data. We believe that MARBLE can be used by the activity recognition community to evaluate novel approaches both for single inhabitant and multi-inhabitant ADLs recognition, but also to investigate novel data association strategies. Due to privacy issues, we were not able to acquire long-term data from actual inhabitants in real homes. However, based on our previous experience in real-world deployments and in the lab data collections, we designed a data collection campaign in a smart home lab, with significant efforts in making it realistic and diverse. This allowed us to make a complete and very accurate annotation. This figure shows how the smart home lab is divided into 6 semantic areas, each representing a different room. Different environmental sensors are deployed to monitor the interaction of the subjects with their surrounding environment. We include magnetic sensors to detect open and close events of different drawers and the fridge, pressure sensors to detect when residents are sitting on chairs or on the couch, and plug sensors to detect the usage of the electric cooker and the television. As wearables, we opt for smartwatches since they have low obtrusiveness, they are becoming quite common, and they can capture hand gestures useful to reveal ADLs like washing the dishes. Since we plan to monitor answering and making phone call activities, the subjects also carried an Android smartphone in their pockets. We developed an Android application in charge of communicating in real-time phone events to our Linux server. MARBLE includes data of 13 different activities: answering phone, clearing table, cooking, eating, entering a living home, making phone call, preparing cold meal, setting up table, taking medicines, using PC, washing dishes and watching TV. This table shows for each activity the amount of recorded labeled data in minutes, the average duration in seconds, and the number of collected instances. Since we had tight restrictions for data collection due to availability of the volunteers, we limited the execution time of each performed ADL to a duration that in some cases does not reflect the actual time a person would actually need, but long enough to obtain a significant amount of labeled data. For instance, considering eating or cooking, we asked our volunteers to perform the ADL only for a few minutes. We carefully designed several single and multi-inhabitant scenarios for data acquisition. Each scenario is a template that describes the type of activities that subjects should perform and their order. Each scenario has been performed several times by different subjects. We designed 4 single inhabitant scenarios, and overall we collected 12 instances of these scenarios. We collected also 10 instances of the 3 designed scenarios that involved 2 subjects. Finally, we designed 4 inhabitant scenarios, and overall we collected 10 instances of them. In the multi-inhabitant scenarios, the subjects concurrently perform both individual and group activities. To introduce high variability in the dataset, we did not specify in details how each activity should have been performed. Hence, the subjects were free to execute the activities in their own way. In order to make data acquisition as realistic as possible, annotation was performed by a different team that was watching live video streams of what was happening in each area of the smart home lab. Each member of the annotation team was in charge of annotating data for a single subject with a different annotation device. To obtain accurate annotations, both the environmental and wearable sensors and the annotation software communicated with the same gateway. This gateway was in charge of providing the timestamps both to the data and the annotations before storing them in a MongoDB database. Clearly, sensor data collected from the smartwatches were automatically associated with the correct subject by the Wear OS application. The members of the annotation team use a dedicated software to annotate in real time the ADL being performed by each subject, the semantic area in which the subject is performing the ADL, and the associations between environmental sensor events and the subjects that triggered them. The last type of annotation is useful to compare novel data association strategies with an ideal association based on ground truth that can be considered as an upper bound. Moreover, this annotation can also be used to isolate the environmental events triggered by each subject in order to evaluate single inhabitant approaches. We implemented and evaluated on MARBLE 3 different neural networks as benchmarks: a fully connected deep neural network (DNN), a convolutional neural network (CNN), and a neural network that combines convolutional and recurrent layers (CNN-LSTM). Inertial and environmental sensors data were temporally aligned and segmented into windows of 6 seconds, with an 80% of overlap. We empirically determined the architecture of the neural networks as well as the size and the overlap factor of the segmentation windows. The two types of data were provided as separate inputs to the networks. For each window of inertial sensors data, we extract a matrix in which each of the 9 rows encodes the measurements of one of the 3 axes of a specific inertial sensor of the smartwatch: accelerometer, gyroscope, and magnetometer. Each row includes LW measurements, where LW is the average number of measurements collected by inertial sensors when the segmentation window size is equal to W seconds. We interpolate missing values or downsample measurements when needed. Then, for each window of environmental sensors, we generate a binary matrix in which each of the 25 rows represents a specific environmental sensor or a specific semantic location of the smart home. Each column represents a specific second within the window. For instance, the third column represents the third second inside the window. The value of the matrix at row E and column J is 1 if the sensor or the location E was active at a second J, 0 otherwise. We trained each of the 3 developed neural networks with the data collected both in single and multi-inhabitant scenarios. We first evaluated these approaches by considering an ideal perfect association between the environmental events and the subjects that triggered them. We adopted 3 well-known evaluation methodologies and a novel methodology that is particularly significant for a multi-inhabitant dataset. The first methodology simply consists of splitting the dataset in 70% for training, 10% for validation, and 20% for testing. The second one is a 10-fold cross-validation. The third one is a leave one subject out cross-validation. At each fold, one subject is used as test set and the remaining subjects as training set. The leave one subject out is generally used to test the generalization capability of the classifier on subjects that did not contribute to labeled data. Finally, we propose a new evaluation methodology that we call the leave one scenario out cross-validation. At each fold, an instance of one of the MARBLE scenarios is used as test set, while the training set excludes both data from instances of the scenario considered in the test set, as well as data related to the subjects that contributed to the test set. This last methodology is the most restrictive one, since it tests the generalization capabilities of the classifier over unseen users and also over sequences of activities not included in the training set. This figure shows that the evaluation methodology has a significant impact on the measured F1 score. We observed that the first evaluation methodology overestimates the recognition rate. By using this methodology, it emerges that CNN-LSTM outperforms the other approaches. However, both the training and the test sets contain data samples related to the same subjects and scenarios. Hence, it is likely that this evaluation methodology suffers from overfitting problems. The 10-fold cross-validation methodology is more robust and it provides a better estimate of the recognition rate. However, at each fold, training and test sets may still include data from the same subjects or scenarios. This type of evaluation confirms that CNN and LSTM reaches the highest recognition rates. Leave one subject out and leave one scenario out methodologies provide a more robust assessment of the recognition rate than the other ones. By using these methodologies, we observe that all the considered approaches reach similar recognition rates. The lower recognition rates reached by these methodologies is due to the fact that our dataset includes activities that are particularly hard to recognize on subjects and scenarios that were not observed during the training phase. This is the confusion matrix obtained with the CNN-LSTM method, evaluated through the 17-10-20 dataset split. We observe that activities like eating, watching TV, and using PC reach high recognition rates. This is due to the fact that these activities can be performed only in specific smart home areas, triggering environmental sensors that are not involved in other activities. Some activities significantly decrease their recognition rate. For instance, clearing table and setting up table are often confused since they share similar inertial signals and the same environmental sensors. Preparing a cold meal is sometimes confused with cooking or washing dishes since all these actions are performed within the kitchen semantic location. This figure shows a comparison between an ideal perfect data association based on ground truth and a naive data association strategy. In particular, we considered a naive method that associates each environmental sensor's event with each subject in the home environment. In order to better highlight the impact of data association, we only considered the environmental sensors and we discarded the activities that are not captured by those sensors in the dataset, like answering phone, entering home, or washing dishes. We also grouped the activities clearing table and setting up table, since it is not possible to discriminate them only by using environmental sensors in our dataset. A perfect data association dramatically affects the recognition rate of some activities. For example, we have an increment of about 40% in terms of F1 score for cooking and using PC. On the other hand, the improvement is lower for those activities that are often performed at the same time by all the subjects of the scenario, like eating or watching TV. The researchers could use the naive strategy we presented as a baseline while evaluating novel data association strategies. At the same time, the recognition rate of the perfect data association could be considered as an upper bound. Finally, since one of the contributions of our dataset is the combination of wearable and environmental sensors, here we show the impact of the inertial sensors data provided by wearable sensors on the recognition rate of each activity. We observe that some activities like washing dishes significantly benefit from wearable sensors data. Indeed, those activities include significant hand gestures that are typical for those activities. As expected, wearable sensor data do not have impact on those activities like watching TV that are monitored by distinctive environmental sensors. In conclusion, today we presented MARBLE, a dataset that includes both wearable and environmental sensors data collected in scenarios where up to 4 residents concurrently and jointly perform activities in the same smart home environment. The purpose of our work is to address the need for more public multi-inhabitant ADLs datasets by the research community. Research groups can use MARBLE to propose new approaches for single and multi-inhabitant ADLs recognition. Moreover, MARBLE can be used to evaluate novel methods for data association, that is still one of the main open challenges of multi-inhabitant settings. The major limitation of MARBLE is that it has not been acquired by continuous monitoring of residents in real homes. However, we dedicated a significant effort in designing realistic scenarios, in leaving freedom in activities execution, and in an accurate data acquisition, making the dataset as realistic as possible. Thanks for your attention.